Okay, so thank you for also the opportunity to lead this discussion. So for the benefit of people that will be following along in YouTube, this is the Art for Data Science book club, and today I'll be discussing chapter 19 of the 3D Modeling with R book, and the chapter is being titled, When Should You Trust Your Predictions, that in which we are getting from the model in which we have developed. So for the learning objective, mainly, basically, the chapter mainly focuses on these two aspects. We're looking at how we can use the equivocal zone use, how we can use equivocal zones to determine if the values in which we are getting from the predicted value, if it actually true or not. So we are also going to see how use the applicable package to quantify how applicable the model is to new data sets. So that is basically the two things which we'll be trying to cover up in our discussion section for this chapter. So first of all, we talk about equivocal. So we need to, the mainly discuss is about this case study, which talk about 51% of chances having contracted COVID-19. So the mainly discuss in this section is that whatever value in which we are getting from our model, we should always try as much as possible to derive draft an equivocal zone. So that equivocal zone should be a zone in which any value that is going, that is equivocal zone simply means those points in which we suspect that the model is not actually doing a good job, that those are false data points in which once we should always draft a zone out. So they first of all start with these logic functions. So, and in this logic function, they were trying to derive 200 data points that they are going to use for the training sets. They also set out 50 data points they are going to use in evaluation of the model. So they basically will be using tidy models. So they define a function which is simulate two classes. So this is how they go about the function. We have this function which takes some parameters, some inputs, some arguments. So we have a sigma, which is a matrix of the range between 1, 0.7, 0.7, and 1. So this basically is a function in which they set a random seed. So they set a training sets, which is simulate two classes. Just as I said, it's just 200 data points that will be used for training the model. And this 50 data points is going to use to evaluate the model. So the problem in which we have in AND, since we're having two classes, so they make use of the logistic regression. So for the logistic regression, the family, they are using STAM because they want to they make use of the Bayesian framework, and then they fit the model on the training data sets. Then they print out the two classes. That is the first 3 rows. So after they print out that, they visualize the output. So and this output in which they visualize here, they have the prediction, which is the Y value. We have also the predictor, which is in the X. Okay, so they now fit a boundary. They cut out a boundary, and each of the data points that fall within those boundaries, those data points, I think they are the correct predictions. So all those data points that falls outside this cutoff line. So that is what they call the equivocal zone. And they do explain here in the book that once we have such a problem, because we can see these are the equivocal data points, because such data points are, if we are deriving predictions, so the values might not be, it will not be accurate. So that we are, it will not give us reliable prediction once we use such data points in making our model. So I don't know if anybody wants to chip in something here before we proceed.
Yes, that's basically the most interesting part, because we are now going to try to separate these points even further to identify which one are the to be allocated on a side more than the other. So that's very interesting point.
Yes, thank you very much for that. So I think the next step there, what they did here, they want to look at, they use the augment two classes, class mode on the testing set. So they view the head. So here we have .pred class. These are all the predicted class we got from the model. Then we have .pred class 1. These are all the values. .pred class 2, the X value, the Y value, and also the class, the actual class. So when we proceed here, we can see that how are we going to, we are going to see how we are going to use the probably package, which is another add-on package that is added in some we are going to see how we use the probably package to derive the equivocal zone. So we have to first of all load the library. So we have levels of the training sets, $ class, which is going to give us all the levels. So we have the pred class, then we say mutate, which is going to create a new column. Then the new column we want to create, I think we have .pred with equivocal zone. We have two class pred, then we have .pred class 1, then we have level, then we have buffer is 0.15. So when we see that, we are seeing that we have an EQ, we are going to have this table, okay? This table gives us the EQ, which is the equivocal zone, which is 9. We have class 1 here is 20. We have class 2, which is 21. So this equivocal zones. So what this zone stands for is the rows that are within 0.50 plus or minus 0.15 are given a value of EQ in this output. So it's going to look at the training set in which the data set in which we are feeding in to this function. So it's just going to flag those rows in which we have the mean between 0.50, which is around 50%, plus or minus 0.15. So it's going to flag it as the equivocal zone. So that equivocal zone is what we saw here in this plot above. Okay, so these are those data points we saw here in this point, in this graph in which I saw. These are the equivocal points. So these equivocal points are the suspected points in which we are not supposed to report that. We need to, because they are suspicious, we are not supposed to report that. So what do we do there? Okay, here they now show this results in a confusion matrix. So this is just a confusion matrix where we have the truth for both class 1 and class 2. We have the prediction for both class 1 and class 2. Here we can see that the truth, okay, for class 1, the true value, the true positive, I think we have a value of 20. While we have false positive, it's going to be like 5. While for class 2, we have 6 for the truth. Then we have 19 here as the, then for the prediction value for class 1, here we have 20. When we put up all this together, we are going to derive the accuracy for that model. We are going to see how we get the accuracy for the model. So here they also do the same thing, the confusion metric for the for the equivocal zone. The prediction we are getting from the equivocal zone. So we are going to get this other outputs. So the function. So in this case here, they said, does the equivocal zone help improve accuracy? Let's look at this. So they want to see if actually the equivocal zone is going to help us to improve the accuracy in which we are getting from the model. So what do we do there? They define another function. So, and this function is taking just a single argument, which is the buffer. We have the test spread, and then they mutate to create a new column. Then they say the accuracy will be test spread, and then accuracy is class dot spread with equivocal zone. So here we're having the reportable rate, which is rep rate, and then we have buffer. So when we use the map function from the POR, in this map function, we have a sequence, the sequence that is going from 0 to dot 1, then the length of output should be 40, and then list row bind, then we have to pivot longer because the data set was in a wide format. So we have all the column except the buffer, then names towards statistics, the values to value, and then we pipe it to ggplot2. Then we are using geom step. And here we can see that the accuracy improved by few percentage points, but we can see how the accuracy increases by just a few percentage points. So this dotted line is just showing us the reportable rates in which we can from the model. Okay, so I think that is that. So this function shows buffer can compute the accuracy, how we can improve accuracy from the model using this effect equivocal zone. I don't know if someone wants to add something before we proceed.
Not for me.
Okay. So what we have again? Okay, so yeah. Okay, yeah, they still make use of the test spread, and then the bind calls, then say predicts, which is 2 class of the mod, and then we have the testing set type. The prediction type, we have spread int, then standard error is set to true. And this now give us a similar plots that we have seen above where I was showing. Here we have the predictor of the X. We also have the predictor of the Y, and we can see that class 1, these are all the class 1. We can see class 2, these are all for the class 2, and also this is a standard error, which shows a level of confidence intervals. So among all this is just one approach in which, but in this case now we have fitted this model. How do we now apply this model into the real world situation? That is where we need to make use of another package, which is called the applicable, because they said equivocal zone try to measure the reliability of a prediction based on the model output. It may be that model statistics such as standard error of prediction cannot measure the impact of extrapolation, and so we need another way to assess this. So that is why we now need to use another tool to see how we can apply this problem in which we have trained the model to another situation. So there, in this case, they make use of the Chicago data sets. I think this data set is coming from the model data package. So from this Chicago data set, they select ridership, dates, and one-off stations. Okay, so they have Chicago train, which is Chicago, and then slice from row 1 to N minus 14 minus, then Chicago test is Chicago, and then slice row n minus 13 to row n. So this is going to be the testing set. This is going to be the training set for the model. So yeah, what they did here, they defined several pre-processing steps in which they define a recipe where we have ridership till the dots, means all the column data is Chicago train, and then step dates for all the dates, and then step holiday for all the dates. So these are all the pre-processing steps in which they define for this, for the recipe, for the base recipe. Then here, what they did here, they fit a linear model. The engine is LM. There's a linear regression, which is, this is the linear model specification. Then they now define a workflow where they now pass in both the model and also the recipe in which they have defined. So here they are fitting the model on the training data set. And then here they make the prediction on the test sets. So here, what they did here, they select the dates, ridership, and start with .pred. So we have dates, ridership, .pred lower interval, and prediction interval for the upper. Okay. So when we have this, we now check for the root mean square error for the prediction, so which is around 0.865, which is quite good. Okay. So, but when they visualize this, we can see we have the time period in the x-axis, daily ridership in the y-axis. So we can see the confidence interval band. We can see that this model fits. We can say that this model fits the data sets very well. But how do we apply this to a new data set? So they will now discuss on how do we apply this model in which we have fitted to a new data set, which is for the June 2020 data set. So what do we do there? The result for 2020. So this is the prediction. So results, and then contains .pred. So we now look at the dates. We look at the predictions we are getting. We have the lower confidence interval. We also have the upper confidence interval. So when we look at that, so result, we select dates, ridership, and start with .pred. So this is what we have. So we check for the root mean square error. Here we are getting 17.2. Remember, initially, this is where we are coming from. We had a root mean square error of 0.865, which is quite good. So, but in this case, in this problem, the root mean square error is around 17.2. So when we now visualize this, we can see the confidence interval. We can see that this does not fit very well. It's not, the model is not doing a good job, because we can see those data points here. We can see the confidence interval here. So we can see that when we apply the same model in which we train to a new data set for 2020, we can see that there is a slight deviation. So I don't know if anybody wants to add something before we proceed. This is where we are coming from. We fitted the model. Okay, we can see the model was doing a very good job here. We can see the confidence interval that the model fits very well. We can see that the root mean square error was quite high. But when we now test this on apply this to a new data set, we can see here we are having a root mean square error of 17.2. The confidence we can see that there's some kind of deviation. So in order for us to fix this problem, I think they discussed that we need to use another techniques, which is the dimension reduction, which is principal component analysis. So here we have in the panel A, we can see the training set data. We have Austin 1 and 2, the x-axis California. We can see that the data sets, they are they're highly correlated to each other. So, but when we perform the principal component, which we can see in panel B, okay, we can see the training set PCS scores. We can see the same trend. We can see that the data sets, they are highly correlated. So when we also plot the component 1 and also component 2, the distances to the center, when we visualize them, that is where we arrive at these plots. Then this is just the distance to the training set center when we look at the reference distribution using a histogram. So we can see we can say the data set is fairly, I think, quite follows a bell curve shape. Yeah. So what do they say here? Okay, so I think here I was trying to look at this. Okay, this is still the distances to the training set center. I think they said this was the test set, which was shown with a dash line. This is the test set, and also the triangle, and this was this circle, red circle, and is for the training. It was a training data set. I think this is a training data set. So here they now look at distance to the training set center when they look at the distribution. So what did they say? They said that from what they explained, they said that 1.28, the test set point distance is 1.28, which is around here, which is this dotted line we are seeing here. It is in the 51.8 percentile of the training set distribution, indicating that this is snugly within the mainstream of the training set. So this is around 1.28. But what is this red line? This red line, I think they explain. Okay, I think there is where they say, okay, that is the extreme point. It indicates that these are the extreme. These are the extreme. Right above is the extreme. So, but in this applicable package in which we can use, because using the PCA, we can also use this applicable, which just make use of this single function, which is APD_PCA. We just say tilde dot means that we are using all the column that can be found in this Chicago train. And then we select one of stations. And then we say threshold is set to 0.99, which is going to mean that we want to use 99.99% confidence. Then we are going to have this output. It's going to tell us the predictors, which is 20. This is what we are feeding in. Then it's going to tell us principal components. It shows the 9th component were needed to capture at least 99% of the total variation in the predictor. We need to make use out of this 20 predictor. We only need how many? We only need a total of 9 components to capture 99% of the total variation that can be found in that data. But when we use the auto plot to visualize the reference distribution, we just need to pass in that PCA start and also the distance. Then we say lapse is distance. So I think we are going to arrive at this plot, which shows the percentile and also the distance, the percentiles and also the distances. What's they do here? Okay, the same thing I've explained. It's just they are just extracting the table. I think that is yep. I think that is all, because the next is just like the chapter summary where we have already seen how we can use the equivocal zones, and also how we can use the applicable package to apply this to unseen data using the principal component analysis approach, which I just showed. Okay, so I think that is that. I don't know if someone wants to add something. Hello, Frederica.
Thank you for presentations. Actually, I was still very confused. That's why I don't have many questions for you. But really, thank you for the great presentation.
Okay, welcome.